Here we go. Thank you very much. Okay. So I was saying, so I will briefly give a succinct overview of CEO, and then I will go in detail through two of the main features where CEO is useful is for ray tracing through the GMT, and then Fourier propagation from the GMT exit pupil down to the focal plane of our sensor, optical sensors. And so that will be both in slides, and then there will a Jupyter notebook that I use to do some interactive demonstration and example and try to answer questions. So I hope this talk will be interactive. So feel free to ask questions, and I will do my best to answer, or even to use a notebook to demonstrate how things are done. All right. So what are the main functionalities of CEO? So it's a geometric optics propagation tool, doing ray tracing à la Zemax kind of. And then you're capable of doing diffraction propagation, but it's only in the limit of Fraunhofer approximation. So there's no Fresnel diffraction like we may need, for example, for coronagraph, where Fresnel diffraction and on each optical surface is a bit critical to have. We cannot do that with CO for now. So I will refer that as Fourier optics propagation. It provides all the GMT optical prescription of our dually segmented mirror. So we have the 14 segments in the model, the 7 segments of the primary and the secondaries. It allows to apply rigid body transformation to each segment independently, so 3 translation, 3 rotation. Useful to close the loop with especially the active optics, which we use to maintain alignment against different perturbation like wind load, thermal and gravity, etc. We can also apply figure error on each segment independently. And then CO contains the complete suite of GMT optical sensor. So I mean, imaging camera, chaque carbon wavefront sensor, pyramid wavefront sensor, dispersed wave sensor, they are all available in the package. And it also comes with an atmospheric optical turbulence model. It's almost obviously that you need that when you model a ground telescope. And also, as I showed earlier this week, it has also a Zemax parser. So we have the ability to take a Zemax optical design and then bring it into CO and use and insert into the design even some of the unique objects that CO provides. That's for the main functionalities of CO. So a bit of about the software. So CO, the core of CO, rely on a CUDA API. So what's CUDA? What does that mean? That means that CO run exclusively on NVIDIA GPUs, and it won't work on anything else. So that's the advantage of that is to be able to do massively parallel computing. A good example of that is ray tracing. Each ray is independent, so there's one thread per ray, which allows to propagate a very large amount of rays through the telescope in a very short time. CO is written in CUDA C++. So, and CUDA is the NVIDIA C++ language add-ons that is provided as an interface to NVIDIA GPU. So it's what allows you to communicate with the GPU and to do this parallel programming. So few people really want to dive into CUDA to do their simulation at first. So CO comes some wrappers. The first one is a Cyton wrapper. Cyton is a compiled Python interface, and it provides exactly the same functionality that you have in CUDA. And yes, in CO CUDA. There may be a few exceptions, but it's almost complete, I would say. And it's what people everybody are using. Inside the modeling, we are we started to use for almost the computing challenges, most heavy computing or the Rust programming language, which kind of a replacement to C++. And we started to have an interface for CEO in Rust that is mostly for the usage of integrated modeling. So, what to find documentation? Well, you can always look at the source code, the first things, but very few people are very enjoy that. But we have a reference manual, which is the source code but documented. So, and let me show you what that looks like. Okay, here is the reference manual. So it's a big document now, which contains all the source code, and it's documented. So here you can see on the left here all the, so there's two parts of it. Let me close it. You see, it comes in two parts: the CEO source code and the Python API that you can. And each one is divided. It has a chapter for each module in CEO. And the same for Python. So if you want to know a bit more what's under the hood of either CUDA or Python, it's available here. And the way I say it's documented, let me show a nice example. Special. This one is nice. So all the CUDA code is written using a programming approach which is called literate programming. So it was an approach which was championed by Donald Knuth, the inventor of TeX, which we know as LaTeX, which was of the opinion that instead of writing code for a machine, we should first write code for a human. A human can understand the code, and then have a parser which takes the code and transform it to something that the machine can understand. And so what that looks like, so for example, if you implement a formula like the atmospheric dispersion that is available in CO, you can really mix text and code together. And you have these weird things here which define chunks of code. And you can interleave that with detailed documentation. Here you have the formula, and for each formula you have both the mathematical expression and the code associated to that. And you have a little chunk of code like this. And then at the end, when you write your final function, like I did here, you put all the chunks together. And then you have a parser which goes through that and will on one side take all the chunks and put them back together. And then you will have your CUDA and C++ code you compile, and then you will have also documentation at the same time. The nice thing of that is that it makes the code a bit easier to read. You tend to have your documentation always in sync with the source code. But when you have two documents, sometimes one is ahead of the other one. Usually documentation lags behind. Because you have both, you're writing both at the same time, they're always in sync, so there's some advantage to that. The main disadvantage is that not many people are familiar with this type of programming, so it's another hurdle. People have to learn CUDA and not too familiar of this approach, so that's maybe the downside of that. So, and everything is like this, so there's for example, if we look at imaging, for example, here, so there's a lot of code, of course, because it's a source code which is there, but you see you have the parameters and descriptions of the parameters are here. What else do we have? It's interesting, a lot of code. You see some convolution, how do we do convolution of the source, and propagation. So there's a bit of explanation. Here you see a bit of explanation of the numerical model, so the Fourier propagator. Everything is described. If you wanted to know how we do ray tracing through the GMT while moving the mirror, I think if you go to GMT mirrors, somewhere here maybe, you can find it quickly. That's something. So, for example, the coordinate system is also described. at the place where at the same place where the code is also defined. So you can collect one to the other. Different coordinate systems are defined here. Okay, that's also an interesting one. You may find it's all the different steps that array goes through into the GMT from the plane where it starts to all the mirrors, the different transformation and so on. So if you really want to understand how ray tracing is performed through the GMT, you will get that from that. So it's not something, I won't say something easy to read, but there's a lot of autonomous information here that it's a big document. and it's, all these details are a bit scattered across the document within the code. So it's not the easiest of read, but take the time, you will learn a lot about how CEO were wanting to introduce that. The Python API, there's a website here where you have, but it's not, I have to, honestly, I didn't have the time to really update that API, that Python documentation recently, so it's probably a bit out of date. I have to take the time to refresh that. But that's available, and as soon as I can, I will update that for everybody. But that's also something which is available online, which is nice, but in fact, I will show you, you get almost all the information you need directly within the Jupyter notebook. So that's why I don't really use that a lot. All right. And here's a Jupyter notebook. So if I go back to GitHub and look at what we have here, I go to the Devel branch, which is the latest version. So there's really two main branches now in CEO, developers master and the Devel. So the master is always the one which reflects the GMT with respect to everything which has been officially released. So coordinate system, size of the mirror, mask, etc. Whereas Devel kind of follows the design almost on a daily basis. So if you want really have the latest updates on the mask, on the baffle, for example, of M2, you will have that on Devel. But if the baffle has not been yet officially released and vetted by the project, it won't make it into master. That's the way. So I think your best bet is always to go to Devel because you have the latest design. But when I sometimes for some reviews where I want to be sure that I am compliant with the current release version of the design, I will go to master. But what I wanted to show you here is that if you go, for example, there's atmosphere, for example. Yeah, you see here you would have some IPython notebook available. So there's a lot of examples like this. In fact, this example have two purposes for me. First, as a test of CEO for me, as I update the code on a regular basis, I rerun this example, making sure I didn't break anything. And then the same are tutorial, how to for users. So that so there's one for the atmosphere. I think there's maybe from the GMT mirrors. Yes, there's a few here. So if you browse that, you will find a lot of notebooks available, not on all of them, but on many of them. So that's something, many directories. So that's something good to be aware of. Documentations. Okay, that's for the documentation. So how do we get started? How do you get started with CEO? So I said that you need GPUs. So you have the option to bring your own GPUs. So it's some of you have done that already. They have their own GPUs in their own institutions, and they have implemented and installed CEO. The installation step are on GitHub, and you have tells you which version of CUDA to use and etc. So you have everything there. Installation usually goes smoothly, except for Python sometimes, depending on the version of Python. Python is a weird thing at some point. Compile CEO, you need to go through inside of Python installation and get from some header files. So you need to know the version of Python that is detected by CEO. But for some reason, for some version of Python, instead of Python 3.6 or 3.8, you will have Python 3.6n. I don't know why there's an M, and then that will throw off the compilation. So it happened to some of you, so please let me know, and I will help you go through the issue. That's the only problem people have mainly. Otherwise, you can use a GMT provided cloud-based GPU machine. So we have a GMT modeling portal like this, and so you can access it. So depending on who's there, if people are not familiar with that, I could maybe the list of people I could explain. Okay, maybe I could show that some people may be interested or how to get started with that. So first you need to identify yourself. So really, I try to explain here what to do. So if you have never used this service before, press the submit button. Okay, let's see if we do that. Okay, so we don't put an email. So it says, sorry, you're not a vetted user yet. Please send a request to me. So you click there, and you get a pre-filled email, and you send it to me, and I will add your email to the database of users for CEO. And then at some point you will receive an email from Amazon, which will ask you to verify your email. And when it's done, then you will be able to access it. So what you have to do, you have to put your email here here, and then first you submit once to get an access code. Okay. So, and then you go check. So check your email for your single-use access code. Yeah, decide not to use password. Password are paying 20 months. So access code. Yes, I did get one. Then here, and then you pass your access code and you select CEO, because there's several applications available to the user, but the one you are in CEO. So with all that, you can submit now. Access granted, and it's starting CEO. So what happened in the background is that it talked with AWS services, and we start the machine, an Amazon machine where you can run CEO, and the machine will come with CEO pre-installed and with Jupyter Notebooks pre-installed. So you have no installation to do. It comes with everything you need. Okay, when the machine is ready, you get the address of the machine. So you open that. Let's see. Sometimes you click that and you get an error message. And the reason why is sometimes the URL, oh, like no, good, that's good because it doesn't fail all the time. I wanted to have an example who fails like this because you may experience that sometimes. So it doesn't mean that the process has failed. What does it mean is that the URL of the machine is ready before the machine. The machine is still initializing. So you will have sometimes to request again the same URL a few times. The second time's work, and then you get into here we are in the cloud. And so to get into Jupyter, the password is CEO uppercase. So easy, CEO uppercase, and you log in. And tada, you are in Jupyter, and you can start to create a new Python 3 notebook. And then ready to go with CEO. So that's the way to get started easily. Everything is there for you. And when you're done, you go to terminal here. Because the machine won't stop by itself. So you can do EC2, and that doesn't work. EC2. So you go home, Ubuntu, bin, EC2 stop, and that stops the machine. Because Amazon charges by the second the machine is on, so I ask people to close the machine when they're done. But I will monitor. I monitor the service. So if I see that a machine stay on a bit too long, I will ask people if they really intend to use that. Close the machine. So just a demo here how to get started. So let's close all that. Let's go back to the presentation.
Rod, how much do we pay per hour for these machines? Just to get a feel for it.
A few dollars per hour.
Okay.
$per hours.
Thanks.
And there are several type of GPU available. I think you start on the least powerful, and when you get used to CO, then you can have request to be on a faster machine. But on the machine, we start with I think the slowest of the GPU, some of the slowest, not the slowest, but some of the slower GPU, which are a bit cheaper. Like this, you can spend more time training yourself without costing too much. Okay, well, now let's start it with CO. Let's have a bit of fun. So starting with ray tracing through the telescope. So here you recognize the optical design of the GMT. So relatively simple, only 2 mirrors, simpler than some optical design that I had to model recently. And so we're going to ray trace through that. So the first thing you need to do is to define a GMT object. And that's how you do it. So you import CO first, and then CO GMT.mx give you a GMT object. MX means that there are several mirrors, M1 and M2 for now. And certainly at some later date we will add M3 too. But for now it's just M1 and M2 on the model. Then you need also to define a source that is going to get propagated through the telescope. So here is how we define the source. Let me explain what are these parameters. So first, we specify the photometric bandwidth. So CO understand the main astronomical photometric bandwidth, and you can even specify your own. If you replace that, for example, by I think it's a tuple, which you specify the wavelength, the spectral bandwidth, and the 0 point, the flux. You will understand that. But the simplest way is to use the predefined one. Then you specify the position in the sky of your source with respect to the optical axis of the telescope. So it's what zenith and azimuth mean. It's with respect to the optical axis of the telescope. And then we need to sample the entrance pupil, which is our primary mirror here. So ray box size and ray box sampling really define you can put a box around your primary mirror, and ray box size, it's the size of your this one side of your box in meter, and ray box sampling is the number of sampling points across the side. That's going to define the number of rays and their spacing, and how you're going to sample the telescope with rays. Rays origin, so what does that mean? The first two coordinates, 0, 0 are XY coordinate, and define the intersection of the chief ray with the entrance pupil, with the primary. So usually we use 0, 0, the chief ray, your bundle of rays is centered on the telescope, but you could, if you want, have an offset. Nobody does that usually, but it's available. And 25 means the distance from your entrance pupil to where the bundle of rays, the rays are coming from, are going to start. And they start, of course, above M2. So if we go back, 25 meters will be about somewhere here. So that means 0, 0 will be here, and 25 will be here, so the rays come down. Okay. Does that make sense? If you have any question, let me know. So once you have your source, you define your optical path, and you can define it like this. So that tells to the source that is going to propagate through the GMT only. And then when you have the optical path, you can then propagate, and you just use this operator plus on the source and then on the propagation. So a very short amount of step to the ray tracing. So now I'm going to switch to Jupyter Notebook to show you live what it looks like. So import CO, import the object, create the source, ray trace, and we can. So when you ray trace is when you ray trace from your source coming down here, to M1, M2, and to the exit pupil. And there you have access to the wavefront, the optical aberration, if any. So yes.
So that syntax of source and then left, angle, GMT, comma. So that syntax, is that a CEO system in syntax? Where does that syntax come from?
Yes, it's something I made up as a shortcut. So it's something I wanted to talk towards the end, but as you mentioned it, I will show you something else now. Mm-hmm. So you have this cheat sheet here, where it's a little bit small for you, the way it's displayed. I don't know if you can see that, but okay. So it gives you for the main objects, the GMT objects, the source and the Shack-Hartmann and the image I'm going to talk in a few minutes, the different ways to realize the same operation. So behind this syntax here, there are some methods which are called. So and these methods are given here. So for example, the optical path, which I set it from a source object here into the GMT, and you can add more, you will see. You can instead call the optical path, set the optical path variable to a tuple of objects. The plus that I showed here, so reset and propagate the wavefront, behind the scene, it does a source preset and a propagate through all the objects of the optical path. So this is syntactic sugar to avoid to have to type a lot of code all the time. At some point I got a bit tired to type all these methods, so I decided to go to overload some operators in Python to be able to do that a bit quickly. So you have that available, and so you can see in this table the different correspondence. The methods, of course, are a bit more powerful, so you can do a bit more things with them. But for this demo, everything can be done with the short syntax. For example, the WFPT bench, I think I only used methods to really reproduce that. There's no equivalent in the short syntax. But this table gives you the equivalent, so you can always come back here and see what is done behind the scene. So I was down to the wavefront here, and so you get the wavefront by reading the source object. So you can get the source phase, and the host. Remember, we are on GPUs, so you need to bring back, and GPU comes with own memory. So you need to bring back data within the GPU memory back to the RAM of your computer, and host does that for you. So phase resides on the disk on the GPU, and when you call host, it brings that back, and you can specify units. Here I want my front in nanometer. In fact, the phase is not really in the source, but in another object within source, which is the wavefront, which has a phase. But the phase is given per default as a 1D vector, and very often we want to have a 2D image, so this is a convenience. This one, in fact, refers to this one and reshape it to have a 2D map. So depending on what you want to do, you can use one or the other if you need a 2D array or 1D vector. And you can get the RMS wavefront error from your wavefront, and optionally you can pass this a parameter here which we multiply the RMS by 10 to the power of this parameter. So this will give you the RMS in nanometer, for example. If we execute that, here there's no aberration in telescope. Telescope is perfectly aligned, so we have less than a nanometer wavefront error, and the error that we see also within 1 nanometer. So perfect telescope here, and there's a bit more you can access from the source. You can access the piston across the whole pupil, or the piston per segment. It can compute the tip tilt on each segment. Segment wavefront gradient is what that gives you. Computing the tip, so very often we need access to that, how much tip tilt we have per segment. And this phase RMS function, in fact, is the same thing as the wavefront RMS, but it has an option where you can specify that you want the phase on the segment. So you can also compute the phase wavefront error RMS, but per segment. So we'll have a loop. So now I'm going to talk about rigid body motion and how you control the segments. Is there any question first on this first ray tracing aspect? If there's no question, I will move on to rigid body motion.
Rod,
Yes?
CEO must have an understanding of which pixels are within the pupil and which pixels are not within the pupil.
Oh, yes. Yes, it's exactly what happened, because it's a very good point. You see, we define an array on a box, so at the end you get this, the vigneting by the segment. So it computes, as the ray trace through its segment, it computes if a ray falls on a segment or outside, and if it's outside. There's okay, that's why I make it interactive. In fact, there's something called source.rays.vigneting. Vigneting.host. And if we look at what probably had to be reshaped, so the vector reshaped, I think it's 512 by 512. 20.show. There you go. You see, so the vigneting. So that's how, as it ray trace through the telescope, CO keep track of which rays intersect a mirror or not. And in fact, the wavefront amplitude is set by the vigneting. It's 1 or 0. That's how it works. And it does that at each propagation. So if you move a segment, the vigneting will be different. And that has been a source of confusion sometimes when you said the first time, because if you move a segment and then you do propagation and you move by a little bit and you make another propagation, you get two wavefronts and you differentiate to take the difference. People see very large pixel on the end and they say, wow, CO is not is doing something wrong. No, it's just because the vigneting is different. So when you do the different two wavefront corresponding to moved segment, you need to take into account the vigneting on both. So you multiply the vigneting and you apply that to both wavefronts. That's a very good point, yeah, because it's a question that arose recently,
Rod, just to be nitpicky, where you plotted this, or you did this in show, I'm not familiar quickly with the Python coloring scheme on the color bar, but the ones are presumably inside the yellows are the ones, in which case it seems counterintuitive. It seems to say everything inside the segment is actually vignetted, or maybe I'm misunderstanding what.
So one means the rays is available. It's not vigneting.
Got it. Great. Great. Thanks.
Yeah. Okay, any other question related to ray tracing? Okay. So I'm going to show you now how to control your segment, how that interact with ray tracing. So for rigid body motion, the main thing you need to know is the coordinate system that we're using to move the segment. So GMT has a coordinate system which is defined for almost everything in the observatory, including M1 and M2. And here I reproduce the local coordinate system of each segment of the primary and secondary. And it's within this coordinate system that you move the segment. So you see when you say we move along a translation along Y for an outer segment, means it's a radial translation. And then it's a tangent, the X in fact is a tangential translation, the same for M2. And tip and tit are also defined in this coordinate system. Right. So it's important to know that. So a bit of demo of how that works. So again, I use my special syntax here to reset the GMT. So this symbol GMT means oops. I will share with you the Python notebook at the end. Reset GMT to pristine. settings, so perfect alignment. And then you have this state variable in GMT which tells you for both which will give you a dictionary which contains M1 and M2, tip, tilt, and rotation and translation, even modes. We'll come back to that. Let's focus on the rigid body motion. So the rotation is an array of 7 by 3. So 7 segments. Rotation is X, Y, and Z, and the same for the translation. Right? And the same applies to M2. I define here the GMT without parameters. So there's no possibility. So there's no mode. Modes correspond to the figure error we apply on the segment. Even if you see some, per default, it puts a vector of 0 here, but it will have no effect here because we didn't define it. Per default, there's no figure error on the applicable onto the segment, only rigid body motion. All right. So and then once we have the state like this, we can write to the state. Let's put a one tilt on the first segment, for example. Here, yes, let's do that. Of 1 arcsecond. So according to the optical sensitivities that we are all aware of for the GMT, we know that we should get about 2 arcseconds of segment tip tilt. And then once you update the state, you can update it like this. GMT and this syntax here will update the GMT state. If you wonder what's happening under the hood, like Vijan was asking, we must have that somewhere here. Yes, you see, you can have this syntax to update and call a few methods here to realize that. So this is just convenience method, which allow you to retype again and again and again the same code. If you spend your time like me simulating CO, this syntax becomes very useful. But you don't have to use it. You can use the methods if you want to get familiar with them. So where I was here, so you update, and then you propagate again the source, and then let's see what we get in. There we go. And you see, so here I print the segment corresponding gradient, the tip tilt per segment, and we see we get almost 2, so as expected on this. Right, and we keep it. We can do the same on M2. On M2, we expect in the exit pupil, if you put 1 arcsecond, a quarter. That on the next segment, and a tilt in the other direction. No, I will put 0, 1, 2, 3. We put this one off for now. Here you go. So I'll put this segment, tip tilt, and you get about a quarter. So I was talking a bit before the system will do that. So if I put, so you see all the tilt over oriented. It's because we stick in Y here. So Y being radial, you have this tilt like that. And if I put along X, it's going to be like that. Okay, it's how you control the rigid body motion of a mirror. The same goes for translation too. Any question related to rigid body motion? Because I'm going to move to
just real quick, there is rotations, translations. What are modes again?
I'm going to do that next.
Oh, gotcha.
Okay, no disappointment. Okay, we'll stay right on the book for that. Segment figure, segment modes. Here we go, Bijan. So here I'm going to show you how to shape your segment. So of course you can do both rigid body motion and figure shaping. I show you one by one, and you can combine. So as I said, there's no parameters given to. Okay, let me start from the beginning. So I started like, before I started like that, just no parameter part. And I told you there's no modes apply to the segment. There's only rigid body motion. Well, I lied. In fact, per default, on M1 and M2, there's a Zernike mode. But the number of modes is 0. So it's like having no modes. But there, the Zernike are available to you. And to tell how many modes you need, for the Zernike, you specify the number of radial orders. You need to be a bit familiar with your Zernike, but if you have 3 radial orders, then you have n plus 1 plus n times n plus 2 divided by 2 modes, which is 10 in that case. You have access to the first 10 modes. And if you do...
Oh, sorry, I was going to say if these are null ordered, but once you specify the radial order and the frequency, I think it's defined. So sorry.
It's defined, yes. Yes, it is.
Yeah.
And so if you, and how you set them is very similar to the, we can look at the state. Here we go. So now the mode, you see, it's an array of 7 times 10. And then you're going to write to these arrays, as I do here. Let's put a comma on segment number 3 of M2, for example. What that means? M2 mode, this is the second segment, sorry, and 7, 6, 8. Get a comma here, and then we update the state, we propagate, and then we look at the aberration. Here we go. It's not a comma. I should know my Zernike, I think. Here we go. This is a comma. So you have access to the Zernike, and the same goes for M1, of course. Can affect the second, the last mode here is what I showed you. Okay. So this one put a Zernike on M1, and this one put a Zernike on M2.
Sorry, I think I missed something. So for Zernike specification, there is the radial order, and then there's the azimuthal.
Yes.
So that's 2 numbers, but here are the indices. There's 1 for the segment, and then how do you get those 2 out of the?
Oh, that's a good question. Yes, I assume some ordering of the Zernikes.
Oh, so you are using ordering, like a null ordered or?
The null. It's based on the null ordering.
Okay, got it.
Yeah, that's
right.
a good question. I'm going to make a note here. Ordering according to null. Like this when ordering according like this when I share that with you, you will have this information according to null. Yeah, that's important to be aware. Otherwise, you wonder a bit what. It's a bit of a guess. Otherwise, what Zernike you're going to get. Okay, but in fact, on the GMT, we rarely use the Zernikes. This is just to show the principle. For M1, we have the bending mode of M1. In fact, where that comes from, we have the finite element model of M1. And we can apply forces on each of the actuators that will be below M1. So we have the influence functions, and we take the eigenmodes of the influence function matrix, and that become our bending modes, right? Almost, we also remove piston tip-til. We don't want the bending mode to create piston tip-til because we can do that with rigid body motion. So you can have bending modes. So the syntax to do that is specify which mode we need. Or here bending modes. And the number of bending modes you want, 27. So it's a bit different with Zernike. Zernike, the radial order is what you need here. So if we do that, and I can command M1, and it's the very first one. The first bending mode is an asymmetrism. So the bending modes are look-alike Zernike for the very first one. When you go to higher orders, you take the last one. It's still almost an aspheric mode. If you zoom a bit more on it, you can see that it's a bit squarish. compared to the old Wernicke, but they are very, very different. If I take more mode, how many do we have? 100 and yeah, I think something. I will go to that and that one. Yeah, you see this one is a bit different. But the recommendation for the GMT is to use 27 Danny mode from people who work on the LBT and for various reasons they explained to us that it's difficult to control more than 27 Danny mode. And for M2, for the ASM, Fernando has built for us Karolynov basis with up to 1,000 modes. So if you want to do adaptive optics, you will use a Karolynov mode, and so it's a similar syntax for M2 than for M1. You specify the mode and the number of modes, and you get your M2. So this is the first Karolynov, like the Wernicke. If you go a bit further, you get something like that. Okay, so that's how you shape the mirror. And as I said earlier, you can combine rigid body motion and figure error together by writing to the state and overwriting the state and editing it. That is the mirror. Okay. I'm going to move to Fourier propagation now, unless there's some question related to shaping the mirror or rigid body motion.
I have a question that's related, which is how do you reproduce a telescope pointing error? Do you offset your source? Is that the way you would do it?
Let me see if I remember to do that. Pointing error azimuth.
Okay.
Pointing error, yeah, this variable you can set.
Okay.
In practice, it does exactly what you're saying. It's moving the source, it's easier. But from the user perspective, you want to have the feeling that you're moving the telescope, so you give access to this variable, right? But you could do this. Pointing error. Yes. And there's also empty pointing azimuth. I keep that here like this. You can. Okay. If there's no further question, I'm going to go to Fourier propagation. I will go back to that here for now to explain a bit Fourier propagation. So with ray tracing, we went to the exit pupil, and now we want to go to the focal plane. So you do that by doing Fourier propagation from here to here, which Fourier propagation really means that. Means you do a Fourier transform of the complex amplitude of your wavefront, taking the phase you get here from ray tracing, and the amplitude is fact 0 or 1. It's based on the dignity. And so, so the main object for that is the imaging class in CO. I'm going to explain a bit this parameter because it's both it's a bit powerful, but then it may look complicated a bit at the beginning. So let's go through these parameters. So first,
Sorry, I have a dumb question. Between M1 and M2, then after that, the M3 are there other optics that are powered, or they're not powered after that? Okay, that's it. Okay.
So yes, so we have different focal station in the GMT. We have the direct narrow field or wide field Gregorian, which is this one, and we have a folded port on top of the platform, which is here. And we have a folded port. So here you will have an M3. This is not in the model yet.
But effectively, it would be just going to
yes.
because it's not powered. Yep.
Yeah. There's no power. It's just a folding mirror. there's no power, but we would like to put it anyway because we expect it to maybe deform under gravity, thermal, etc. So probably we will have a shape to put on it, polishing mirror and this kind of thing. So at some point we would like to have it in the model, but we don't have too much detail about this M3 mirror yet. So that's why it's not in the model. But I think at some point it will make it straight. But for now there's nothing. So that's why it goes straight.
Thanks.
Okay, what are these parameters? So NPX pupil. So if you remember earlier, we specify here the size of this bulb will be 512. And my imager is 511 pupil size, which is this size here, because I think it will make more sense for the next slide, but I will explain rapidly now. Maybe a bit too weird at the beginning, but bear with me. 512 is a number of points, so the vertex of the grid, which is all these points, and 511 is a number of bins, so it's always -1. Right? The NPX image, it's the number of pixels in the image plane we're going to use. So the image will be 32 by 32. Okay. DFT OSS. So that means discrete Fourier transform over sampling factor. Basically, what it is, it's used to making sure that you don't transgress the Shannon theorem. So at least you want 2 or more to have a better resolution. That's why if you go less than 2, you're going to have more, because we do discrete Fourier transform, you're most likely going to have numerical aliasing. So less than 2, danger. If you go there, you need to know what you're doing. Right? So per default is 2, and you can. I will show you what happens when you increase this number, but I won't go below than that. You can bin your image on the detector. So at the end, your resolution will be NPX image divided by the binning factor, and your pixel size is going to your wavelength divided by the pupil size that we define for the source. Divided by this oversampling factor and multiplied by the binning image. Get some used to it, I know, but you will see how show you how that works. And then to combine together ray tracing and Fourier propagation, you redefine your optical path with the GMT and the imager, and then you propagate with them. And you do both ray tracing and Fourier propagation. Let's see how that works. Fourier propagation. So here I redefine my pupil with 5 to 512 pixels. The source is defined the same way than before. Nothing has changed. Now I introduce the imager object I defined here, and then the optical path. Oops. Optical path. I reset the GMT because I don't redefine the GMT, so I don't know if I may have modified it. The shape and the rigid body motion, so everything is back to perfect ideal mirror, and I propagate. And if I do that, here is a focal plane image of the GMT, and you can get the pixel scale here in arc second. I give it in arc second, and you see we have a 32 by 32 image coming from that. If I were to change, for example, the DFT-OTF, we increase the resolution. And the image is 32 by 32. We could increase the image here, okay. And we could bin to go back to lower resolution. Okay. So we can have all this. I think as we're progressing, why is defined like this, and how to play, how this number are used to start from an imager specification, which is the pixel scale, the number of the resolution of the detector, this kind of thing, and how you start from this specification and define this number to match the specification and become more obvious as we progress. I will show you an example. Okay.
Rod, I have a question.
Yes.
So I apologize if this was already asked because I called in late, but does the simulation take into account orthogonal, does it separate orthogonal polarizations?
There's no polarization modeling.
Do, do, have, do we think that the polarization effects on the coatings of the mirrors will have a phase shift that's large enough that we care about it, or it's insignificant?
I am not sure. Some things definitely for coronagraphy you want to have a look at.
Yes.
But
That's why I'm asking.
yes, but yes, I'm not sure honestly, like what can be the effect here
Okay.
on coronagraphy, and this not in the model right now.
So I guess
Right, thanks.
I would ask the team, like people like Antonin and Marcos, to think about whether this makes a difference to the phase sensing or not.
No, I don't see why polarization would affect your phasing at all.
For
Okay.
phasing, I don't think so.
Okay. Thanks.
I will move on. I have a few slides about Fourier propagation, and I will stop and we can ask me questions because I think things may become a bit more clearer or obvious as I progress. So bear with me for a few slides. All right. So what is very kind of ubiquitous in our line of work is lens-led array. Jacquard front sensors are almost everywhere. So that was important to be able to reproduce propagation through a lens-led array. I'm going to show it next here. In fact, the same object imaging do that. In fact, imaging it's contain a lenslet array. So before I was using only one lenslet, but now we are going to show you how to start to use more lenslet array, a real lenslet array. So here I just have an example with a 2x2 to explain a bit the parameter. So only parameter we change is the side. I think this is okay. Is the number of lenslets. So n-side lenslet means that you have a 2x2 lenslet array. I'll show it here. The n-px pupil, in fact, is not the beam across the whole pupil, but it's per lenslet. So it's visible square. So remember, we have stopping points from edge to edge, each vertex here. So the number of beam is going to be the pupil sampling, which go from all the points from edge to edge, from that edge to that edge, minus 1 divided by the number of lenslets. Quite easy to get convinced of that. So n-px pupil is a pupil per lenslet. N-px image is the same. It's also the size of the image, but the image formed by each lenslet. DFT OSF and beam image are the same meaning. So the detector resolution is going to be now is going to be n-side lenslet times n-px image, because n-px image is per lenslet divided by the binning factor if it's larger than 1, and the pixel size it's now it's lambda over what we call sometimes small d, so the pupil size divided by the number of lenslets. So it's what you have here, and then you have this 2 factor again. I have an example of that works afterwards here. Maybe yes. But before that, in fact, I realized 256 here. I'll modify that later. Anyway, here is an example of this 2x2 on the GMT. So we define the number of lenslet and number of pixel per lenslet in the exit pupil. So when we say n-px lenslet, it's really pupil, the number of pixel at that level, and when you see, where is it, n-px image, it's at the number of pixel at that level. Right? So the pupil, according to the relationship between the number of lenslet and the number of pixel per lenslet in the pupil, the Raybox sampling usually is defined like this: the number of lenslet, so 2 here times the number of pixel per lenslet plus 1, and then this is passed here, n-side lenslet, n-px pupil, 32, etc., etc. And then we propagate. And now we get a 2 by 2 images. I hope that makes sense. Yeah. I may pause a minute and ask if you have any question.
Hey, Rod.
Jesse.
If you request for a larger field of view than is possible given the resolution,
Yes, in that case, yes. The field of view is right. Yes, the field of view is defined by the pixel scale by the size of the image. In fact, the
So
size of
if
it
I request
divided by that. So if you increase the size of the image here, you get a larger field of view. Let me do it again. So 32 by 22 pixels. You get a larger field of view by increasing the number of pixels in your detector.
And
so you see,
okay.
we have 60. So let me do it again. 30. You're right. It's important. So you see, we have 32 pixels per lens set on the detector. So that's why we have 64 by 64, and that gives us this field of view here of 142 mass. And then if you want to double that, you can double the size of the detector like this. So now we have 128 by 128, and the field of view is twice what was before for the same pixel scale, of course.
So there's an upper limit on that, which is dictated by the pixel size in the pupil plane.
Yes, exactly.
So if you request a field of view which is larger than that upper limit, is it going to be padded by zeros, or will it wrap around?
It will be padded by zeros. Let me demonstrate. That's a very good question again. So here we have a pupil of 256 by 256. So if you remember our DFT work, to not transverse Shannon theorem, we do a zero padding A50. So we multiply, we have our wavefront defined on 250 by 250 grid, and because DFTS is factor 2, we increase that by a factor 2 on both sides. If this factor DFT OSF were 4, it would be 4 times bigger. So that means that at the end, for that particular case, you have a 512 by 512 image available to you to convert that into a detector. So I could go, so if you do 512, oh yeah, it's good. So it's slow to respond. The big FFT, so maybe that's why it's taking some time. I should probably do an example on a smaller. It's done. Okay, it's just so you have now a 1024 by 1024 image. But if you go beyond that, let me do something a bit more reasonable, because otherwise it's too long to do it. So back to the same example. Okay. And if we go beyond that, it still works. But it's padded with 0. You have 0 outside, so it's 0 padding. If it's if the size of the detector is bigger than what is allowed by the sampling in your exit pupil.
Thanks.
Okay. Any other question related to how this imaging class works? It's important because it's at the heart of many things that we will doing. We will doing Shekarman wavefront sensing, for example. It will. Okay.
I have a question, Rod.
Yes.
Are you handling broadband light here, or what do you do?
No, it's monochromatic.
So for like the DFS sensor, how do you handle?
It's within the DFS model that I do the dispersion. So it's a bit weird. I specify a monochromatic light source and that the DFS, you specify a spectral bandwidth, and then center on that wavelength you specify, it disperses the fringes.
And here you're showing propagation from pupil to the far field. Can you do intermediate planes as well, or is it?
No.
Okay.
Okay, so then I wanted to show an example next. So for example, if you want to produce a Shekarman 48 by 48 of the GWS, so how would you do that based on what I just said? So what do we know? We know, of course, that we have 44 by 44 letter array. We know the wavelength we're going to use it. We want to have a pixel size of about 0.4 hexagon, and we want about 8 pixels on the detector per lenslet. So we have this expression that I took earlier, for the pixel size as a function of the wavelength, the number of lenslets, the pupil size, which here I choose it 25.5 meters, so just encompassing the segmented M1. Beam image and DFT OSF. And DFT OSF, we're going to use 2 here. So we know everything, the pixel, the number of lenslets, the wavelength, the pupil size, but we don't know beam image. So if you plug all these parameters here and solve for beam image, you get something about 3. That means that when you define your imager, and we'll talk about waveform sensing soon, and you will see very similar. You specify your beam first to 3, DF2SF, which is 2. The number of NPX image. So this is before binning. So we want 8 detectors per pixel times 3, 24. The number of pixels on the pupil. So you have more freedom to choose a bit what you want, but you want to make sure that this parameter multiplied by DOFS is at least equal or larger than the number of pixels. Otherwise, you're going to pad with zeros, and then it's a bit weird. And then the number of them. Okay. Any question on the process here to define that?
I do have one. What's the limitation? So if you've sampled your pupil with 512 rays here, right?
So, in fact, once you define that, this is going to dictate the sampling of your pupil. Let me show you. It's a little bit more obvious on the notebook here. So you specify the lens. There's a relationship you see between pupil sampling and NPX pupil.
Okay.
Here. So there's a relationship you need to respect that. Otherwise, you're going to have very funny images. You see. So. Yes, so for example, in the Revoke sampling, here is defined as a function of the number of lenslets and number of pixels plus lenslet plus 1. It's really derived from this expression here for that. Here, when you define an imager, because of the properties and mechanism of discrete Fourier transform, then that dictates your sampling in the pupil. And here is an example of what that gives you when you do that and get the HWS here. If you were not respecting that, I think it doesn't crash. So if you keep, if you do, for example, 512 like before. And it crashed. Sometimes it crashed and it doesn't crash. So we succeed in crashing here because we didn't do the right thing. Let me restart. Restart. Run. Pulse. On all the boot status. It us exactly where we were. I'm going to restart everything. Okay. All right. So we went through ray tracing and Fourier Fourier propagations. About 15 minutes left. Okay, so I have a few things more to share, but it's really what I wanted to show you and spend more time because it's really a summary slide, I think, after that here on the presentation where we went through the source, the GMTMX and the imaging object are really the fundamentals classes of CEU. And everything else more or less follows of that. It may not always obvious in Python, but in CUDA below, everything relies on that. It's important to understand that. Objects like the Shackman, the pyramid, or the dispersed field sensor, all relies on the source and on the imaging object to do propagation and get you to images. Okay. So now we're going to go through the notebook and I show you a few more capabilities of CO, and unless you want to have a more question on the propagation. If not, I want to talk about first multiple sources. What if you have an asterism, multiple sources you want to propagate through the telescope? Well, CO is really designed to handle that quite well and in parallel. In fact, you do the ray tracing in parallel. You have one ray per core on the GPU. So if you have n source, you have n times source, n number of rays times the number of source, total number of rays, and each one get on a given core. And the FFT also on the lenslet array. So we have as many discrete Fourier transform as lenslet. And each one is batched and sent in parallel with GPUs, and this is multiplied by the number of sources. So as an example here, how do you define multiple sources? The simplest way is to define an array for the zenith angle, so the position of your source in the sky with respect to the optical axis, an array for a zenith. So here I define 10 sources based from by one arc minute from 0 to 10, from really to the edge of the field of view of the GMT. So it's really on the line like this on the center of that. And then a simple imager here, which would be diffractionally limited. And if you do that, I saw that the computation became a bit slower. And the reason is why it's the same GPU which is managed the display on Blue Jeans that doing the computation. So that's why I didn't redefine the GMT. So let's do that. So yeah, so it's going to be slower than it used to be when Blue Jean is not on. GMT equals GMT. The Jupyter a bit slower. Here we go. Finish computation. So usually it's an example which showcase how fast CEO is. It's not going to work on my laptop here with Blue Jean on, unfortunately, because there's two competing processes requesting resources from the GPU. So it's going to be slower than usual, unfortunately. Maybe if I stop my camera for a minute, that may help. I will stop my camera, see if that help a little bit. But it's really slow right now, which is not the case usually. Okay. Okay, let's do something else. Let's request a machine on the cloud if my laptop is giving up. Oh, it's done. Okay. Well, let's continue for now. So he computed what he needs to compute, and here you see the astigmatism as a function of the field of view. So we know that we have an astigmatisms, and the telescope is grow as a square of the field is what we're seeing here, and we also compute the images here, and here you go. So that's from 1 arc-minute to 10 arc-minute how the image degrade because of this astigmatism, and you can do that in CO. Usually quite quickly, unless you overload your GPU like I'm doing now. All right? So it's relatively simple. Everything is the same. You just specify your source, your object with arrays instead of scalar. Basically, that's what you need to do. Something that we probably all need, and it's a bit different from the rest, it's the atmospheric turbulence model. There's a different way to define it here. I will use the GMT atmosphere. It's called the GMT atmosphere because it uses, per default, the CN square profile to have 7 layers, CN square profile for the GMT, which is the standard atmosphere for the modeling of the GMT. So I recommend to use that one. And it takes several parameters. The main one are the R0, the frit parameter, the Hauteur scale. And you need to specify the size of the phase screen at the ground. And from that, you can define, depending on the field of view, you're going to be able to define the size of the other phase screen and the number of pixels to sample this phase screen on the ground. So it's very similar to what I was talking about this box here. Here. So the red box size is equivalent to the L here, and the red box sampling is equivalent to the X-ray pupil, but for a phase screen, which has to be it has to be equal in terms of size of at least the size of the pupil if you want to have a phase screen on the whole pupil or a bit more. And then you specify for the time length, how long you want to play this phase screen of dynamic. And then it's going to pre-compute the phase screen. It's going to take some time, apparently, with this GPU, which is overloaded.
So, Rod, it's a single large phase screen that you transport through the beam. Is that correct?
Yes. In fact, it's seven phase screens because there are 7 layers, and they all have a wind speed and a wind direction, and they move. Yeah, it takes much more time than usual, unfortunately. So I can show you then what happened behind the scenes. So it's something you don't see on the cloud, but you can see on your machine. At the console with Star Jupiter, you will have the CEO objects are computing some information here. So sometimes you want to check that if you have some question. So for example, here it shows you the detail of the atmospheric model. So the wavelength of the R0, the R0, the L0, and the different altitude and of the computer, and the wind speed and the wind direction, for example. The imaging device also gives you some information about pupil sampling, etc. Okay, finished. So let's move on to the atmosphere. And so now, how do you propagate through the atmosphere? So we start the same way here with our source object here. Everything is defined the same. You can here just to illustrate, you can also specify the magnitude of the source just by specifying the magnitude. But what is important is here I specify sampling time because it's dynamic. So each time we're going to do propagation, we're going to do step through the atmosphere. We're going to illustrate that. So let's do one step. Okay, and here is the phase screen. In the source object, there's a timestamp, which is 1 millisecond because we did one step. If I do that, if I do another step here. Oh, Yeah, here I do something a bit different. But you see, I will explain in a minute. This is the source here, and then the time step now is 2 milliseconds. Next step. So it's how you move the atmosphere as you go as you step through your atmosphere. And I forgot to say I redefine the imager, and you can add your atmosphere inside your optical path. Something interesting to note is I put the atmosphere after the GMT. The atmosphere comes first, it plays from first for the atmosphere. It's because the atmosphere is added in the exit pupil of the telescope. It's what usually we do. For example, we do adaptive stimulation. It's fine for most of our application, but we have to remind ourselves that M2 is not conjugated to the ground; it's conjugated to an altitude. So that, for example, will not reproduce a correction if you have a layer which is correct, which is conjugated to your M2, and you are off axis. You won't reproduce what should happen perfectly with that model. That's something to remind. Most of the time, you don't care too much about that, but it's something to be aware because there are some corner cases, especially when you start to think about GLAO, where that may matter. So something to remind yourself. There's always sometimes some limitation, and this is one of them to remind. It's not a major one, but it's something to be aware of for some of your applications. And what if you want to do a long exposure? So you see the imager, I forgot to mention, if I do that several times, if you look at the amplitude, the intensity, it increases. In fact, the imager is integrating all the time until you reset it with that little tilde. And if you reset it, then it starts with, so it's accumulating, integrating the frame all the time. So if you want to do a long exposure, for example, because here we have a single speckle image, we can use this syntax. Instead of a plus, you put for the source, you put the plus on the other side, and you can do plus 10, and you're going to integrate, or 200, and you're going to have a long exposure image integrated so you're stepping through the atmosphere, and you're integrating through the on the detector at the same time. So you can start to form a long exposure, seeing limited images. So that's how that works too. 4 minutes left. So I will skip that. That's interesting. What that shows quickly is how it shows that you can specify the field of view. And I was showing how you can propagate multiple sources at the same time through the atmosphere and have 3 sources. But I would like to, maybe if some people want to start beyond. No, I'm confused. I'm already beyond my time, right? Yeah, a lot. I was supposed to end up at what time? Yeah, I'm already beyond my time. But I should have done at 2:30. Okay. So let's say it's fast for 1.5 hours. And so I don't describe that I will just I won't execute it. I will just show what it says. It's propagation through several sources through the atmosphere at the same time, and I'll show you that. But I wanted to show you the Shakardman waveform sensing finished. So it's really based on the imaging camera that I showed earlier, plus some data processing to get a centroid, right? So you define your source the same way. So you define the number of lenslets, number of pixels per lenslet. In fact, here what I define is like before the SH48 of the HWS. And I added a few things that I'm going to explain here in a minute. Otherwise, the parameters are similar. Number of lenslets, number of pixels per lenslet in the exit pupil, the number of pixels in the detector and focal plane before binning, the binning, etc. DFT OSF here, Nyquist factor is 2, and a few other things I'm going to explain. So if you do that, find out this, and then we can propagate like we do everything else. So just like on that for now, just like that. So you get, so it's very similar to the imaging, but you will see you have a bit more power under the hood here. But something I wanted to illustrate here is this is the diffraction limit on the lens set. So the Fourier max of the image of the lens set compared to the size of the pixel scale of the camera that we set at 0.4 arcsecond. So the pixel is much larger than your diffraction limit of your imagelet, I like to call that, or lens set. So doing soft reading with that is going to create some issues. But we know that for the HWS, we're going to have thing limited image at the focal plane of the detector. So to reproduce that, we can define the Fourier max of the source, and then have Fourier max now, which is a few times the pixel scale, the 0.4 arcsecond. So I do that first. So here I zoom on one part of the detector. So this is very boxy, but if I multiply by this factor, which is expressed in pixel before binning. So 6 pixels before binning. The binning is a factor of 3, so it's 2 pixels after binning, and the pixel scale is 0.4, so the Fourier max will be 0.8. We do that. And I forgot something. It didn't work because I forgot to reset my wavefront sensor. Remember, the imaging camera is integrating all the time, so I was integrating an image where all the light were concentrated in a few pixels with an image where the light will be spread, so you don't see the spread. So if I reset it, you start to see it. It's a bit. If you put 0, it's like having no convolution by anybody. And the image shape is a Gaussian, it's a convolution by Gaussian. You see, and if I exaggerate a bit, you start to see. All right, so that's how you reproduce it. You want to be about 6 here for the G, right? Okay. Centroiding. I'm only going over time. Sorry about that. So what you do with the Shackleton wavefront sensor, first you want to set the reference slopes and the valid lens set. You want to keep the one which has the most light. So 0.75 here, it's a fraction of, we're going to keep the lenslet with light is at least 75% or more of a fully illuminated lenslet. So if you do, here we go. So here gives you the mask. If I change that, select a bit more lenslet. But doing twice the calibration mess up with everything, so I'm going to go to 75%. Okay. Getting the centroid after that. You get a centroid with a negative instead of a plus. You do the wavefront sensor. You can have a plus or a minus before your wavefront sensor, are two different things. The minus will compute the centroid, but because we have calibrated, then we get 0. So if we put some aberration on the telescope, some tip tilt here, and you do that, remember this is a derivative of the tilt, which is a constant. Right? So that's what you get in that. Here, if I do a plus, it works the same. So what's the difference? So if I increase the magnitude to 20, for example, and do the plus, we don't have enough light. Plus, add detector noise. In that case, photon noise. And the flux, and that's why the exposure time is important, because the photometry is computed for a given exposure time. Right? Photoelectron gain also it's a factor you can use to account for the loss of light through your detector, but all your system, your optical system. And the last thing, and you can also specify the readout noise on the detector. You can even specify the background noise, but I won't recommend to use it until I double check it recently. It will give you noise, but Marcos has looked at it recently and told me that it doesn't give him the amount of noise he was expecting. So I have to double check what's going on. But you will get some noise from background noise, but I'm not sure it's the correct number. Just look about readout noise. How do we check readout noise? Because it's combined. So we can reset the wavefront sensor and just do, so we have no light, and then we just read out the detector without light. So we just get without noise in that case. We do that. But plus, and if you look at this, we get 0. So what's happening in the plus also, it's reading the frame, computing the centroid, but also resetting the frame to 0, so you don't get it. And sometimes we don't want that. We want to have the noisy frame available. So in fact, there's a ghost frame of, which is also available, which is, we save the frame there. So you get, and here you have the noise, and if you compute the standard deviation of this one, you get 1 is what you put. And I will stop there because I was way away. If you have any questions, I will take any questions anyway.
Rod, I'm assuming you also have like a reconstructor that you can plug in, and then you can control the
yes.
M1 and M2.
So you have to do that yourself. So you need to calibrate your modes. So with all this machinery that I have described, so for example, you see, for example, here, I compute the tip tilt. I apply tip tilt to M1 and M2. So you can save the centroids and put that in a matrix, and then taking the inverse, you can then have your constructor that way, for example. That you have to do that yourself. You provide you the components to build your own system, but you still have to build it. Something I wanted to mention too is that the calibration is always without noise. Even if I define noise in my object, it won't take that into account. So the calibration is always noiseless in that case. Okay, that's good.
You convolving with a Gaussian, that's just for the calibration, right?
No, as long as you keep this parameter stay forever. So unless you change it back to 0 to have no convolution, I'm using it afterwards.
Okay.
But that's a good point. If you want to see the impact on your system of having a calibration source of a given size, and then later on have a single images of a different size, you could do that by changing this before and after the calibration, for example. Any other questions? Everybody is exhausted, I understand. Okay, well, thank you very much for indulging me so long. I'm going to release you now. Have fun with you.
Thanks a lot.
Thank you.
Thank you. It's awesome.
Okay, take care, everybody. So I will share the information later.